Hello students, so continuing the topic redox reaction, this is our second lecture and we are going to discuss in this lecture the balancing of redox reaction. In first lecture we discussed about the fundamentals of redox reaction. We learned oxidation number and then we applied that in identifying the reagents undergoing oxidation and reduction in a complicated redox reaction. So now we understand in a reaction what is oxidizing agent, what is reducing agent, and we can identify them. The second step in redox reaction is the balancing of redox reaction. Balancing of redox reaction cannot be done randomly by the method of trial, because redox reactions are not simple in terms of balancing. So there is a proper method for balancing of a redox reaction. There are several methods developed so far for the balancing of redox reaction, and different people uses different methods of balancing of redox reaction. But the ultimate objective is to get a balanced redox reaction. We will be taking one, the most comprehensive and the most widespread used method of balancing, and we will try to balance the redox reaction using that comprehensive method of balancing of a redox reaction. Once we go through all this, at the end I will let you know a shortcut method of balancing of a redox reaction also, using which you can balance any redox reaction in not more than 30 seconds, that I assure you. And balancing of redox reaction will be used in the next part of this chapter, that is to solve the stoichiometry of a redox reaction. So we are going to start balancing of a redox reaction. Balancing of a redox reaction. As I have just said, that balancing is done using a proper method, a proper technique. The one is oxidation number method, which is mentioned there in NCERT book also. But we would prefer a better method, which is also there in NCERT book, that is ion-electron method. So we are going to balance a redox reaction using ion-electron method. This is the most comprehensive method of balancing a redox reaction, and once understood, it is the most convenient also to use. So better to learn the method which is comprehensive as well as easier to use. So ion-electron method, what we are going to do, there are certain steps used in this method and they must be used in a proper sequence also. So what we are going to do, we are going to take a case of redox reaction and will be applying all those steps on that redox reaction simultaneously, so that at the end when we complete the methods, we'll have a balanced redox reaction at hand. So let us take a redox reaction, say KMnO4, K2C2O4 H2SO4 giving MnSO4 plus CO2 plus K2SO4 plus H2O. Now we want to balance this redox reaction using ion-electron method. As the name appears, ion-electron method, this method is applied on ionic reaction, a reaction in which ions are involved. So our first job is to transform a redox reaction if given in neutral form into ionic form. Means here we have all the neutral compounds, net charge on all compounds are 0. So we must first convert this into an ionic reaction if we want to balance it. When converting it into ionic equation, we consider only those ions who are undergoing change in oxidation number. We leave those ions who are not involved in the redox process, in which oxidation numbers are constant, not undergoing any change. So in the previous lecture, we have seen a lot of examples for identifying the compounds undergoing change in oxidation number that can be used now. In this reaction, manganese is undergoing change in oxidation number from +7 to +2. So when transforming this into ionic equation, we'll have to take ions from this. In potassium oxalate, carbon is in +3 oxidation state and it is also undergoing change to +4. So ions from oxalate will also have to be taken. So if we take the ions undergoing change in oxidation number to write an ionic equation, we would write the equation MnO4 minus plus C2O4 2 minus. So the ions involved in oxidation reduction process here is permanganate ion, not the potassium ion, oxalate ion, not the potassium ion. And then we'll have to write the corresponding products in ionic form. So permanganate is undergoing change to Mn2+. If one of the ions or a compound undergoing change producing a covalent compound, it will have to be taken as such because it cannot be written in ionic form. So CO2 will be taken as such. Now the first step is, we call it step 1. Resolve this redox reaction into two half reaction, oxidation and reduction half reaction. If we see in this reaction, manganese is undergoing reduction +7 to +2 and carbon is undergoing oxidation +3 to +4. So in the two half reaction, one half reaction will consist of permanganate giving manganese, another half reaction will consist oxalate giving CO2. So first we resolve this redox reaction into two half reaction like this. That is the first step. MnO4 minus giving Mn2 plus and oxalate ion giving CO2. In step 2, we can also add here, it is reduction, decrease in oxidation number of manganese, and the second one is oxidation, increase in oxidation number of carbon. The second step, step 2, is balance the element. This step is balance the elements other than hydrogen and oxygen. Balance the element other than hydrogen and oxygen. In first reaction we have manganese other than hydrogen oxygen, so it is already balanced 1-1. In second reaction we have carbon, so other than hydrogen oxygen, so 2 carbon must be balanced by giving 2 on this side. It will be better if we write these 2 reactions separately, so that we will keep on applying the steps on this. So MnO4 minus now giving Mn2 plus and C2O4 2 minus giving 2CO2. Then comes the third step, this is very important. Third and fourth step are the most important in balancing of a redox reaction. Third step we call oxidation number balancing. Balance the change in oxidation number. Balance the change in oxidation number per formula unit of oxidizing agent and reducing agent by adding electrons to the side higher in oxidation number. What we are saying? Balance the change in oxidation number per formula unit of oxidizing agent and reducing agent by adding electrons on the side higher in oxidation number. This is very important. Let us try to understand. Balance the change in oxidation number. If we take the first reaction of permanganate giving Mn2 plus, we see that MnO4 minus giving Mn2 plus per formula unit, means for 1 unit of oxidizing agent, and in 1 unit of oxidizing agent we have 1 manganese only. So we'll have to find out the change in oxidation number for 1 manganese in order to account for 1 formula unit. And here the manganese is +7 oxidation state. On the right side it is in +2 oxidation state. So difference is of 5 electrons, difference is of 5 unit of charge. The difference in charge must be balanced by adding electrons on the side higher in oxidation number. So on this side we need to add 5 electrons. This is called oxidation number balancing. If we take the second reaction, what we see in oxalate ion, individual carbon is in +3 oxidation state on the left side, carbon is in +4 oxidation state on the right side. But we need to balance the change in oxidation number for 1 unit of oxalate, and 1 unit of oxalate contain 2 carbon. So on 2 carbon, which is part of 1 formula unit of oxalate, we have a total of 6 positive charge on the left side, and so on 2 carbon we'll have 2 into +4, 8 unit of charge on the right side, and there is a difference of 2, 8 minus 6, 2. That difference has to be balanced, not the difference in oxidation number of carbon atom, which is 3 to 4, 1 nahi. 1 unit, 1 ion of oxalate will be considered in balancing the change in oxidation number. So it is 6 to 8, so 2 electron needs to be applied on the side higher in oxidation number. So if we apply these steps on the reactions, we see 5 electrons, on the left side of permanganate and 2 electrons on the right side of oxalate reaction. So this step is applied. Then comes the fourth step. Step 4. These two are the backbone of balancing, step 3 and step 4. This is called charge balancing. Charge balancing. The two half reactions must have balanced charge, means charge must be equal on the two sides of reaction. Balancing of charge depends on the medium of the reaction. Redox reactions always occur in some specific medium, which can be either acidic or basic, or in some cases even the neutral medium also. So it is the medium which determine how the charge will be balanced. Presently we have taken reactions occurring in acidic medium, so we will apply that, and then in the next example we will take the redox reaction occurring in basic medium. So in acidic medium, balance the higher charge by adding hydrogen ion on opposite side, and finally balance hydrogen and oxygen using water. What we have to do, we have to make the charge equal on the two sides of half reaction, and if the medium is acidic, higher charge, the side which is higher in charge will be balanced. Means what we'll have to do, we'll have to check the charge on the two sides of half reaction, and the side which has higher charge will determine that this will be the charge on the two sides of a reaction. Let us apply this on the example we are taking now. So if we take the first reaction, 5 electron plus MnO4 minus giving Mn plus 2. If we determine the total charge on the right side, it is plus 2. If we determine the total charge on the left side, it is minus 6, minus 5, minus 1, minus 6. So this side is higher. So in acidic medium, there should be plus 2 charge on both sides, higher charge on both sides. So in order to make this plus 2, we'll have to add plus 8. Plus 8 unit of charge will have to be added on left side, and that will be done using 8 hydrogen ion. So after this we'll have minus 6 and plus 8, so total plus 2, and that will be equal to charge on the two sides. So what we need to do, we need to find out the charge on the two sides, and higher charge should be equated on the two sides, means higher charge will be the charge on the two sides, and on the side lower in charge, hydrogen ion is added to make the charge equal on the two sides. So that is how we balance the charge in a half reaction. Second reaction has already balanced charge, minus 2, CO2 0, so 2 electron minus 2, minus 2, minus 2. So it is already balanced in the second reaction. We'll write the rule here for basic medium also, but we will be applying that in the second example. One thing we left, balancing of hydrogen and oxygen. So we have seen 8 hydrogen ion on the left side. So if we add 8 hydrogen ion, now we balance hydrogen oxygen. What we have to do, we have to see the number of hydrogen on the two sides. The side deficient in hydrogen, balance the hydrogen by using water. So 8 hydrogen, right, 4 water. Now oxygen will automatically be balanced. In second reaction, hydrogen oxygens are already balanced. There is no hydrogen, 4 oxygen, 2 into 2, 4 oxygen already balanced. Had the medium be basic, in basic medium, balance the lower charge by adding hydroxide ion on the opposite side, and finally balance hydrogen and oxygen using water. So in basic medium, what we'll do, we'll find the charge, we'll find out the charge on the two sides and the lower side charge. Charge on the lower side will be equated on the two sides, smaller charge will be equated on the two sides using hydroxide ion. Like we did in the acidic medium, we equated higher charge, greater charge on the two sides using hydrogen ion. In basic medium, smaller charge will be equated on the two sides using hydroxide ion. That we'll see in the next example. Then the last and the final step, which we call step 5, equalization of electrons in the two-half reaction. Make electrons equal in two-half reaction by multiplying with a smallest constant and add the two half reactions to obtain the balanced reaction. What we'll have to do, we'll have to make the electrons in the two half reaction equal so that when we add them, the electrons get cancelled. And we can see that here we have 5 electrons, here we have 2 electrons. So if we multiply this by 5 and this by 2, then there would be 2 into 5, 10 electrons, 5 into 2, 10 electrons. Electrons will cancel off. If we do this, we'll obtain almost balanced redox reaction. What we'll obtain? 2MnO4 minus 2MnO4 minus plus 5C2O4 2 minus plus 16H plus giving 2Mn2 plus 10CO2 plus 2 into 4, 8 water. So this is almost balanced redox reaction. Why I am saying almost? That this is the balanced redox reaction in ionic form. Now we'll have to convert this back to neutral form, and for doing that, what we need to do, we just need to compare the coefficient of balanced redox reaction with unbalanced redox reaction. Just pick up the coefficients here and put it into the unbalanced reaction. What we obtain? 2KMnO4 plus 5K2C2O4 plus C 16H plus 16 hydrogen ion will come from 8 sulfuric acid. So 8H2SO4 gives 2MnSO4 plus 10CO2 plus 8H2O. After this, we find some of the ions are not balanced. especially the ions which is not taking part in redox reaction. Potassium will not be balanced in this reaction, but potassium can now easily be balanced through inspection. On left side, the coefficients are fixed for the compounds which contain potassium. So we can count them. 2 potassium here, 5 into 2, 10 potassium here. So 5 into 2, 10 plus 2, 12. On the right side, 12 potassium will be adjusted by writing 6K2SO4, and now this reaction is 100% balanced. So this is how we balance a redox reaction using ion-electron methods. So in ion-electron method, there are 5 important steps. Step 1, resolve the redox reaction into reduction and oxidation half reaction. Balance the element other than hydrogen and oxygen. So we balanced manganese and carbon. Balance the oxidation number, change in oxidation number, and the important thing was that we balance the change in oxidation number for one unit, one formula unit of oxidizing and reducing agent. Then charge balancing in acidic medium, basic medium, we have seen how to do it. And then finally we make the electrons equals, and ultimately we get the balanced redox reaction. So next, we are going to do a lot of practice to apply this. This can be mastered only through practice. We need to do a lot of practice, then only we'll be able to balance a redox reaction with confidence. And I must remind you what is going to be the objective of this redox reaction. You will be asked that how many moles of potassium oxalate, how many moles of potassium oxalate can be oxidized by 1 mole of potassium permanganate in acidic medium. There you balance this redox reaction and then apply the concepts of mole, that 2 moles of potassium permanganate oxidizes 5 moles of potassium oxalate. So 1 mole will oxidize 5 by 2, 2.5 moles of potassium oxalate. This is one example. There are several this type of situations which have been asked in IIT JEE and will be asked in IIT JEE. So balancing is going to be the backbone of this redox reaction. This will be the most important part of redox reaction. So let us do some more practice on balancing of a redox reaction using ion-electron method first, and once we are through, we are confident with ion-electron method, then as I told you, I will explain you a very straightforward shortcut method for balancing a redox reaction, using which you will become the master of redox reaction. You will be able to balance any redox reaction in not more than 30 seconds. That is my assurance to all of you. So now let us take a redox reaction like K2Cr2O7 plus CH3CH2OH in H2SO4 giving Cr2 2SO4 whole 3 plus CH3COOH plus K2SO4 plus H2O. Now we want to balance this redox reaction using ion-electron method. As we all know, in this potassium dichromate, chromium is in +6 oxidation state. If we determine the oxidation number of carbon here, we see 3 plus 3, 6 hydrogen, so +6. For 6 hydrogen, +6, 1 oxygen, -2. So +6 -2 +4, so -4 on 2 carbon. So each carbon is in -2 oxidation state. On the right side, chromium here is in +3 oxidation state and carbon is in 0 oxidation state. 3 plus 1, 4 hydrogen plus 4, 2 oxygen minus 4, so plus 4 minus 4, 0, so oxidation number of both carbon is 0. When writing the half reaction, we will be using ions for ionic compound and covalent compound will be taken as such. So in this compound, the ions we need to write is dichromate ion. And now we can directly start writing half reactions. So dichromate ion is giving +3, it is undergoing reduction, and ethanol is undergoing oxidation. Ethanol is undergoing oxidation to acetic acid. After writing half reaction, what we do first? We balance the elements other than hydrogen and oxygen. So in the first reaction, other than hydrogen oxygen is chromium. Here we have 2 chromium, so it must be balanced. And it is always recommended that you maintain coefficient 1 here. Why? We have to take 1 unit for balancing the oxidation number, change in oxidation number. In this we have 2 carbon, so already elements are balanced. Now the important job is step 3, change in oxidation number. Change in oxidation number. 1 chromium is in +6 oxidation state, but we have here 2 chromium. So for 1 unit we will have to balance the change in oxidation number for 2 chromium. And on 2 chromium we will have 6 into 2, 12. On the right side we have 2 into 3, 6. So 12 to 6, difference of 6. Difference in oxidation number is balanced by adding electrons on the side higher in oxidation number. So 6 electrons will be added this side. In this compound we have 2 carbon and 1 carbon is in -2 oxidation state. So 2 carbon is -2 into 2, -4 oxidation state. On the right side, each carbon is 0, so total is also 0. So difference of 4 for 1 molecule of ethanol, not for 1 carbon, 1 molecule of ethanol. Difference is of 4 and higher side is 0, so 4 electron will be added on the higher side. So now charge is so oxidation number is balanced. The next is charge balancing. If we determine the charge, we see in the first reaction we have 2 into plus 3 plus 6 charge. Here we have minus 2 and minus 6 minus 8. So charge is on this side plus 6, on this side it is minus 8. In acidic medium, higher charge, greater charge is equated. So plus 6 of the first reaction is greater charge, and that must be same on both sides. So in order to make plus 6 on left side, we'll have to add 14. So that will be done by adding 14 hydrogen ion. So now the charge is balanced. So 14 plus 14 minus 8 plus 6 plus 6. In second reaction, charge is minus 4 on right, 0 on left. So 0 should be on both sides. For that purpose, 4 hydrogen ion will be added on the right side. So now charge is balanced. Now hydrogen oxygen, here we have 14 hydrogen. So 7 water on the right side. In the second reaction, better we take oxygen. Hydrogens are at several places. Oxygen. Here we have 2 oxygen, 1 oxygen. 1 oxygen less than on the right side. So add 1 water. Hydrogen oxygen is also balanced. Now make the number of electrons equal. We have 6 electron here, 4 electron here. So first reaction will be multiplied by 2, second reaction by 3, 2 into 6, 12, 3 into 4, 12, and then add them. What we obtain? 2 dichromate, 2 3 ethanol, what about hydrogen ion? 2 into 14, 28, 3 into 4, 12. So 16 hydrogen ion will be here. 14 into 2, 28, 4 into 3, 12. So 28 minus 12, 16 hydrogen ion. What about water? 2 into 7, 14, 3. So 9 water will be on the right side. On the right side, there will be 2 into 2, 4, Cr plus 3, 3 acetic acid, and 2 into 7, 14, 3, so 14 minus 3, 11 H2O. Now compare the coefficient. Compare the coefficient. When you compare the coefficient, you'll find a balanced redox reaction, 2 dichromate. So 2 K2Cr2O7 plus 3 ethanol. For 16H plus 8H2SO4, giving 4 chromium, and chromium is in the form of Cr2SO4 whole 3. So 2 is here in the formula. So if we take 2 of this, 4 chromium will come. So 2 Cr2SO4 whole 3 plus 3 acetic acid plus 11H2O plus potassium will have to be balanced. Here we have 2 into 2, 4 potassium, which must be balanced by writing here 2K2SO4, and now it is a perfectly balanced redox reaction. So let us take some more example for balancing of redox reaction. So some more example for balancing of redox reaction we are going to take here. Now let us take a redox reaction for balancing purpose. K2CrO4 plus SO2 plus H2SO4 giving Cr2SO4 whole 3 plus K2SO4 plus water. In this redox reaction, what we see, sulfur is in SO2 as well as in SO4, H2SO4 also. But on right side, we have all sulfur as sulfate. So among sulfates of the product, some sulfates are directly from H2SO4 and some formed from SO2. And in SO2, sulfur is in +4 oxidation state. In sulfate, all sulfur are in +6 oxidation state. So sulfur of SO2 is getting oxidized, and chromium of potassium chromate are getting reduced. Chromium +6 on right side, +3. So if we split this into two half reaction, what we obtain, chromate ion giving Cr+3, reduction half reaction, SO2 giving SO4 2 minus, oxidation half reaction. Balance the elements other than hydrogen and oxygen, already balanced. Chromium 1 1 both sides, sulfur 1 1 both sides. Change in oxidation number. For one chromium only we will have to balance, +6 to +3, difference of 3, so on higher side 3 electron, +4 to +6, difference of 2, so 2 electron on higher side. Charge balance, again acidic medium. So charge +3 -5, -3 -2 -5, -5 +3, higher charge +3 -5. How -5 can become +3? By adding 8. So 8 hydrogen ion. Now charge is balanced. -5 +8 +3 +3. In the second reaction, 0 -4. So in order to make 0, 4H plus. Charge is balanced. Charge is now balanced. Balance hydrogen oxygen. 8 hydrogen, so 4 water, 4 hydrogen, so 2 water. Now equalize the electrons, make the number of electrons equal in two half reactions. In first half reaction we have 3 electron, in second half reaction we have 2 electron. There is no common factor between 2 and 3. So first reaction should be multiplied by 2 and second by 3. So 2 into 3, 6, 3 into 2, 6. Add them. 2 chromate, 3 SO2. Hydrogen ion. 2 into 8, 16. 3 into 4, 12. So 16 minus 12, 4H plus will be on the left side. Water, 2 into 4, 8. 3 into 2, 6. So 2 water will be on the right side. Gives 2 Cr plus 3 plus 3 SO4 2 minus plus 2 into 4 8, 3 into 2 6, so 2 water. Now let us compare the coefficient. Sorry, 3 SO2, we missed here 3. So let us compare the coefficient. 2 chromate, so 2 K2CrO4. 3 SO2, 3 SO2. 4H plus, so 2 H2SO4. Gives 2 chromium, so Cr2SO4 whole 3, 2 chromiums already balanced. Sulfate, we won't be writing sulfate now, we'll be writing sulfate at the end. 2 H2O. Why we are not taking sulfate from the valence reaction? Because there are two sources of sulfate. Some sulfates are coming from H2SO4, some from SO2. So now chromium is balanced. Now balance the potassium because the coefficient here is fixed, 2K2. So 2K2SO4. Now I think everything is balanced. Chromium balanced, potassium balanced. Let us count the sulfur. 3 sulfur in SO2, 2 sulfur in SO4. So 3, 2, 5. We have 3 sulfur here in sulfate and 2 sulfur here. The rest, everything is balanced. So this is how we balance this redox reaction. One more example. Let us take balancing of glucose by potassium permanganate. Let us take balancing of glucose C6H12O6 using KMnO4 in acidic medium, giving CO2 plus MnSO4 plus K2SO4 plus H2O. It is clear that manganese is undergoing reduction from +7 to +2. In glucose, oxidation number of carbon is 0. Oxidation number of carbon is 0 because 6 oxygen minus 12, 12 hydrogen plus 12, so plus 12 minus 12 0, so carbon is 0. On right side we have carbon in +4 oxidation state. So glucose is undergoing oxidation and manganese is undergoing reduction. If we split this reaction, into half reactions, what we obtain? MnO4 minus giving Mn2 plus and glucose C6H12 O6 giving CO2. Balance the elements other than hydrogen and oxygen. Manganese is already balanced, 1 1. Carbon, we have 6 carbon here, so we need to write 6 CO2. So elements are balanced now in these two reactions. Now change in oxidation number. We have already balanced this reaction so many times, so 7 to 2, 5 electron on the higher side. 7 to 2, so difference of 5 electron on the higher side. In the second reaction, we have 0 charge on 6, 0 oxidation number or 0 charge on 6 carbon, but on right side we have plus 4 on 1 carbon. So for 6 carbon, plus 4 into 6, 24. So 0 to 24. So 24 electron will be added on the right side. So oxidation number is now balanced. Then charge balancing. चार्ज बैलेंस करते हैं. फर्स्ट रिएक्शन में on right side we have plus 2, on left side we have minus 6. So plus 2 should be equated, medium is acidic, so minus 6 will become plus 2 on adding 8H plus. In the second reaction we have 0 on left, minus 24 on right. So in order to make 0 higher charge equal, we'll have to add 24 hydrogen ion on the right side. Now balance hydrogen and oxygen. So 8 hydrogen will be balanced by 4 water and 24 hydrogen will be balanced by 12 water. Now make the number of electrons equal. There is no common factor between 5 and 24. So first reaction will be multiplied by 24 and second reaction will be multiplied by 5. And then add them. When we add them, we obtain 24 permagnetine, 24 permagnetine, 5 glucose, what about hydrogen ion? We have 24 into 8, 24 into 8, 188. No, 24 into 8, 192. 192 hydrogen, 192 hydrogen ion, and here 24 into 5, 120. So 192 minus 120. So 72 hydrogen ion. What about water? 24 into 4, 96, 5 into 12, 60. So 36 water will be on the right side. 24 manganese ion, 5 into 6, 30 CO2, and then we counted water, 24 into 4, 96, 5 into 12, 60, so 36 water. When we compare the coefficient, we obtain 24 potassium permanganate, 5 glucose, 72 hydrogen ion will come from 36 sulfuric acid. On the right we have 24 manganese sulfate, 30 CO2, 36 water, and potassium will be balanced by inspection. So 24 potassium, so 12 K2SO4. One can see what are the possible coefficients in a redox reaction, and this can be obtained by proper method only. This cannot be obtained by methods of trial. So now let us take some redox reaction occurring in basic medium. So far we have taken redox reaction occurring in acidic medium only. So let us take some redox reaction occurring in basic medium and try to balance them, how the redox reactions are balanced in basic medium. Let us take an example of potassium permanganate reacting with Ki giving MnO2 plus I2 plus KOH. Water will also come. Now, how do we know that this reaction is occurring in basic medium? In this reaction, we have KOH. Don't confuse that KOH is a product. KOH is in the medium, and for balancing it may come on any side. That doesn't matter. KOH is not product. KOH is medium. So now manganese is undergoing change from +7 to +4 reduction. Iodine -1 to 0 oxidation. Like we did before, half reactions. So MnO4 minus gives MnO2 and I minus gives I2. Balance the element other than hydrogen, oxygen. Manganese 1, already balanced. Iodine 1, so better you balance for 1 unit of oxidizing and reducing agent. It could also be done by multiplying here 2, but better I used to maintain 1 on this side. That will help us in later discussion also. Oxidation number. In first reaction, we have difference of 3, 7 to 4. So difference of 3. 3 electrons will be added on higher oxidation number side. So on this side, 3 electron. In second reaction, -1 to 0. This is higher side. So 1 electron minus 1 to 0. Now charge balancing. This time smaller charge, lower charge will be balanced. Lower charge, the side which has smaller charge, will be balanced by using hydroxide and the opposite side. So here we have minus 4. Here we have total minus 4, minus 3, minus 1, minus 4. On other side we have 0. So this side is lower, and this minus 4 smaller charge should be equated in basic medium. So on right side we will have to make minus 4, it is now 0. So 4OH minus will make minus 4 on both sides. In the second reaction, charge is already balanced, minus 1, minus 1. Then hydrogen oxygen, we have 4 hydrogen, so 2 water, there is no hydrogen oxygen in the second reaction. Equalize the number of electrons, 3 electrons, multiply it by 3 and add them. What we obtain? MnO4 minus plus 3I minus plus 2H2O gives MnO2 plus 3 by 2 iodine plus 4OH minus. Now compare the coefficient. So there will be 1 KMnO4, coefficient is 1 here. So KMnO4 plus 3 Ki plus 2H2O giving MnO2 3 by 2 I2 and 4 KOH. So it is the balanced redox reaction in basic medium. Usually question is asked to balance the redox reaction with smallest whole number coefficient. Sorry, smallest whole number coefficient. So if some fraction comes in the reaction, that is eliminated by multiplying with the smallest constant factor. So if we multiply it by 2, we obtain 2 KMnO4, 6 Ki, 4 water, giving 2 MnO2, 3 I2, 8 KOH, and this is the perfectly balanced redox reaction with the smallest whole number coefficient. So that is how we balance a redox reaction in basic medium. Let us take few more examples of balancing a redox reaction in basic medium. So let us take 1 or 2 more examples of balancing redox reaction in basic medium, so that we would be comfortable in balancing redox reaction in both acidic and basic medium. Let us take balancing of zinc with NaNO3 in water giving ZnOH whole twice plus NH4NO3 plus NaOH Once again, NaOH is coming on the right side, but doesn't matter. Medium can be on any side. Why NaOH is coming on right side? Here we have NaNO3, so sodium will be balanced by using NaOH on the right side. Now, if we can see, zinc is getting oxidized. Plus, sorry, 0 elemental state, 0 to plus 2 on this side. Nitrogen here is in plus 5 oxidation state. In ammonium nitrate, if we use the concepts of oxidation number, which is average charge, we find that nitrogen, here we have 2 nitrogen, so 4 hydrogen plus 4, 3 oxygen minus 6. 4 oxygen plus 4, 3 oxygen minus 6. So plus 4 minus 6 minus 2. So plus 2 on 2 nitrogens. So each nitrogen can be assigned plus 1 oxidation number. Although the 2 nitrogen are in different oxidation state, but oxidation number is average charge. So we have determined this plus 1. Now if we separate it, then we'll write zinc giving Zn2 plus or ZnOH whole 2 both can be written. Let us take Zn2 plus. Nitrate ion giving ammonium nitrate. Here we have to be very careful. If you write nitrate giving ammonium ion only, then oxidation number of nitrogen in ammonium ion will be determined separately, not including nitrate. But here we have determined plus 1 by taking average on 2 nitrogen, so this must be taken. That is important. Now balance the element other than hydrogen, oxygen. Zinc is already balanced. Nitrogen, here we have 1, here we have 2, so we can write 1 by 2. Change in oxidation number, 0 to plus 2, so 2 electron on the right side. Here we have plus 5 and here we have plus 1. Plus 1 on 1 nitrogen, so 2 nitrogen plus 2 divided by 2, 1. So 5 to 1, difference of 4. So 4 electron here. Now charge balancing. Charge of the first reaction is already balanced, 0 plus 2 minus 2, 0. In the second reaction we have minus 4 minus 1, minus 5, 0. Medium is basic, so smaller charge must be equated. So minus 5 on the other side will make minus 5 using 5 hydroxide ion. Now hydrogen, oxygen. Here we have 3 oxygen, here we have 3 plus 5, 8 oxygen. So using 5H2O will balance both hydrogen and oxygen. 3, 5, 8, 3, 5, 8, 5 into 2, 10 hydrogen, 4 by 2, 2 hydrogen, 5, 7 hydrogen. So hydrogen are not balanced. Just wait a moment, something wrong is going on. 5 and 4, 5 to 7 hydrogen. 7 by 2, something wrong, 4, minus 1, minus 5, so minus 5, charge is balanced. How hydrogen and oxygen can be balanced? Just one second. Here we have minus 4 minus 1 minus 5. On the right side we have minus 5. Now charge is balanced. How many hydrogen we have on the right side? We have 4 upon 2, 2 hydrogen here, 5 hydrogen here, 7 hydrogen, and 5, 3, 8 oxygen. So how the hydrogen is going to be balanced? If we balance 5 hydrogen to 7 hydrogen, then oxygen will not be balanced. Something wrong has gone in this. Let us do differently. It cannot be balanced in this way. So zinc is giving ZnOH whole twice, and let us take nitrate only. Nitrate is giving ammonium ion only. Now 0 to plus 2, so 2 electron plus 5 to minus 3. X plus 4 is plus 1, so x will be minus 3. This cannot be done. We'll have to take ammonium ion separately. Nitrate, so there is no change in nitrate, so leave nitrate for now. So plus 5 to minus 3 reduction, difference of 8. So 8 electron will be on the left side. 8 electron on the left side. Now balance the charge. Here we have 0, minus 2. So minus 2 on the left side also, and that will be through 2OH minus. Hydrogen oxygen already balanced, 2 oxygen, 2 hydrogen, 2 hydroxide here. Here we have minus 8 and minus 1, minus 9 and plus 1. So plus 1 can be made minus 9 by adding 10OH minus. Now balance the oxygen and hydrogen. Here we have 10 oxygen, 3 oxygen, 7 less, so 7H2O. So hydrogen is balanced, 7 into 2, 14, 4, 10, 14, balanced. Water, balanced. Now equalize the electrons. 2 electrons, so multiply it by 4. 4 into 2, 8, 8 electron, and add them. What we obtain? 4 zinc plus a nitrate ion. What about hydroxide ion? 4 into 2, 8, 10. So 2 hydroxide will come on the right side. What about water? 7 water on the left side. 7H2O. Giving 4 ZnOH whole twice. 4 ZnOH whole twice plus ammonium ion plus 4 into 2, 8 hydroxide, 10 hydroxide, so 2 hydroxide ion. But since In this reaction, ammonium ion exists in the form of nitrate. So this ammonium ion will have to be written as ammonium nitrate. So as many ammonium ions are there, equal number of nitrate ions will be required, which is not involved in redox process. Nitrate to nitrate, no redox. So we have one ammonium, we would add one nitrate on both sides, keeping in view that this nitrate is not undergoing change. This is just coming to balance the charge of ammonium ion. Had it been here 2, we would have added 2 nitrate on both sides. Had it been here 5, we would have added 5 nitrate on the 2 sides. So now we add this to obtain the redox reaction. So 4 zinc, 2 nitrate will be written 2Na NO3 7H2O giving 4 ZnOH whole twice plus ammonium nitrate plus 2NaOH, and now it is perfectly balanced redox reaction in basic medium. So this way we balance the redox reaction in basic medium. Let us take one more example of balancing a redox reaction in basic medium. Let us take an example of balancing aluminum plus KNO3 giving KAlO2 plus ammonia plus water, and KOH I am writing over the arrow. It would be decided after balancing on which side KOH should come. So here we have aluminum from 0 to plus 3, nitrogen, this is oxidation of aluminum, nitrogen plus 5 to minus 3 reduction. So if we write the half reaction, we would obtain aluminum giving AlO2 minus and nitrate ion giving ammonia. Balance the element other than hydrogen and oxygen, already balanced. Balance the change in oxidation number 0 to plus 3, so 3 electron plus 5 to minus 3, plus 5 to minus 3, difference of 8, so 8 electron on the left side, higher side. Charge balance 0 minus 4, so minus 4 on this side also, lower charge, 4 hydroxide, minus 9, so minus 9 on this side also, 9 OH minus, hydrogen oxygen, 4 oxygen, 2 oxygen, so 2 water to balance the remaining oxygen, 3 oxygen, 9 oxygen, so 6 more oxygen required on left side to balance the oxygen. Hydrogen is already balanced, 6 into 2, 12, 3 plus 9, 2. Equalize the electrons, make the electrons equal in 2 reactions. So this reaction must be multiplied by 8 and this by 3. Add them. 8 aluminum plus 3 nitrate plus, what about hydroxide? 8 into 4, 32, and 9 into 3, 27. So 27, so 5 hydroxide on left side. What about water? 8 into 2, 16, 3 into 6, 18. So 2 water on the left side. On the right side, 8 eliminate LO2 minus plus 3 ammonia. That's all. 3 into 9, 27, 8 into 4, 32. So OH is on the left side. Now compare the coefficient. So 8 aluminum plus 3 KNO3 plus 5 KOH plus 2 H2O will give 8 KAlO2 plus 3 ammonia, and now it is balanced. 8 aluminum, 3 nitrogen, hydrogen oxygens are all balanced. So that is how we balance a redox reaction in basic medium. Now the question arises that can we balance a disproportionation reaction in this manner? Because in disproportionation reaction there is only one reagent which undergo change. The answer is yes. That has to be balanced, and that there must be some way out. And in the beginning I told you that this is the most comprehensive method of balancing, so it can be used to, it should balance all redox reaction. It would balance disproportionation reaction also. So let us try to understand how we balance a disproportionation redox reaction using an ion-electron method. So disproportionation reactions balancing, how it is done. Let us start with a simple one. Bromine reacting with NaOH to give NaBr and NaBrO3 water. So in this reaction bromine is oxidized as well as reduced. Bromine is undergoing change in oxidation number from 0 to -1 reduction plus 5 oxidation. So what we do, we write the two half reactions in which the reactants are same, identical. So we'll write bromine giving bromide, bromine giving bromate. Next, balance the element other than hydrogen, oxygen. So 2Br2, 2Br2, 2Br minus, Br2, 2Bro3 minus. Change in oxidation number 0, and for 1 unit 2 Br will be considered here. So 2 into -1 -2. So 0 to -2 reduction, gain of 2 electron, plus 5 on 1 bromine, so on 2 bromine, plus 10 oxidation, 0 to plus 10, loss of 10 electron, oxidation. Then charge balancing. -2, -2 balanced. -2, -10, -12. -12, medium is basic. -12, 0. So on this side also the charge should be -12, and that can be done only by adding 12 hydroxide ion. Now balance the hydrogen oxygen. In first reaction there is no hydrogen oxygen. In second reaction we have 12 oxygen on this side, 2 into 3, 6 oxygen, so 6 less, 6 water will balance that. Now make the electrons equal, 10 electrons, 2 electrons, so multiply it by 5. Add them. While adding, reactants are same in both half reaction, so write them collectively at one place. 5 Br2 plus 1 Br2, 6 Br2 plus 12 hydroxide ion, giving 10 bromide plus 2 bromate plus 6 H2O. Also we can see that in this reaction there is a common factor of 2 in the entire reaction, so we can drop that. So it will be 3, 6, 5, 1 and 3. And then compare the coefficient. So 3 Br2 plus 6 NaOH gives 5 NaBr plus NaBrO3 plus 3 H2O. So the disproportionation reaction can also be balanced very easily using this method. Let us take few more examples for balancing of disproportionation reaction. Let us take an example of S8 plus KOH giving K2S plus K2SO3 plus H2O. In this reaction, we can again see sulfur is going from 0 to -2 and plus 4, -6 plus 2 minus 4, so plus 4. 0 to -2 reduction, 0 to +4 oxidation. So it is disproportionation, sulfur is oxidized and reduced simultaneously. How to balance it? We write half reaction, S8 giving S2 minus, S8 giving SO3 2 minus. Balance the element other than hydrogen oxygen, 8 sulfur, so 8 sulfur, so 8. Change in oxidation number, 0 minus 16, so 16 electron on the left side, it is reduction. 0 to 8 into plus 4, 32, 0 to 32, so 32 electron on the right side. Charge balancing, -16, -16, already balanced. Here we have 8 into 2, -16 and -32, -48. So -48 on the left side also, and 48 OH minus. Now oxygen hydrogen, So 48 hydrogen, 24 H2O. Now make the electrons equal and add them. Multiply it by 2, add them. 2s8 plus s8, 3s8 plus 48 OH minus gives 16S2 minus plus 8SO3 minus 2 minus plus 24 H2O. If we compare the coefficient to be obtained, 3S8 plus 48 KOH gives 16 K2S plus 8 K2SO3 plus 24 H2O. It is now a balanced redox reaction. So using ion-electron method, the disproportionation can also be balanced. Then we have seen some redox reaction in which more than one elements of a reagent are simultaneously oxidized or reduced. How to balance them? Suppose we have a reaction Cu2S plus KMnO4 plus H2SO4 giving CuSO4 plus MnSO4 plus SO2 plus K2SO4 plus water. What we can see in this reaction, on left side copper is in +1 oxidation state, on right side it is in +2 oxidation state. Sulfur here is -2. In SO2, which is the product of the reaction, it is +4. Manganese +7 +2. So of this cuprous sulfide, both copper and sulfur are getting oxidized. Two elements are now getting oxidized, whereas manganese alone is undergoing reduction. What we'll have to do, we'll have to write the two oxidation reaction, oxidation of copper and oxidation of sulfur first together like this. Copper is oxidized, sulfur is also oxidized. They are the two oxidation reaction and one reduction reaction, permanganate to Mn2+. Then we'll have to make the coefficient here same as the number of atoms in the compound, original compound. So in original compound there is 2 copper, 1 sulfur, 2:1 ratio. So we'll have to maintain that here. So 2 must be taken here. Sulfur 1, so 1. And then balance this 2 oxidation half reaction up to oxidation number method, up to electrons. So we have here 2 into +1 +2 +4, so loss of 2 electron, -2 +4 -2 plus 4, so loss of 6 electrons, and add them like this. Combine them to form this compound. So Cu2S giving 2Cu2 plus SO2 plus 8 electron, and this we call resultant oxidation reaction. So we need, for balancing, one oxidation, one reduction reaction. If more than one elements are oxidized, take all those oxidation reactions together to form a resultant oxidation reaction like this. Reduction reaction is known, we have used so many times. So MnO4 minus giving Mn2 plus. It is reduction, so gain of 5 electron. Now balance the charge. In first reaction we have 2 into 2 plus 4 minus 8 plus 4 minus 8. So minus 4, 0. Medium is acidic, higher charge will be balanced. So 0 on the other side is also required. So plus 4 minus 8 minus 4, so 4H plus. In this minus 6 plus 2, so plus 2 on the left, so 8H plus, 8H plus, 4H2O, 4H plus, so 2H2O. Make the electrons equal and add them. Equalize the electrons. Multiply it by 8. Multiply it by 5. So 5 into 8, 40. 8 into 5, 40. Add them. So we will obtain 5 Cu2S. 5 Cu2S plus 8 MnO4 minus, what about water? 5 into 2, 10, 8 into 4, 32. So 22 water will come on right side. What about H plus? 5 into 4, 20, 8 into 8, 64. So 64 minus 20. So 44 H plus gives 5 into 2, 10 Cu2 plus 8 Mn2 plus 5 into 1, 5 SO2 plus 5 into 2, 10 water, 8 into 4, 32 water, so 22 water. Now compare the coefficient. So 5 Cu2S plus 8 KMnO4 plus 44H plus from 22 H2SO4 given 10 CuSO4, 8 MnSO4, 5 SO2, 22 H2O, and potassium will be balanced by inspection. So we have 8 potassium, so 4 K2SO4 also. And this is 100% balanced redox reaction. So redox reaction in which more than one elements are oxidized can also be balanced by this method. So we have discussed exhaustively in this lecture how to balance different type of redox reaction under different conditions. And we have seen the complexity of redox reaction. So once again we can say that redox reaction cannot be balanced without proper method. Now I am going to tell you a shortcut method which can be used but with due caution for fast balancing of a redox reaction. And there will be no exception to that my method that can be applied to any redox reaction for the purpose of balancing. So let us take that technique of fast balancing of a redox reaction, which I call shortcut method for balancing a redox reaction. Let us take a redox reaction where we will apply the method. So KMnO4 reacting with K2C2O4 in H2SO4 to give MnSO4 CO2 K2SO4 and water. Our task is to solve the stoichiometry of this reaction, and for that we require a balanced redox reaction, and we have just discussed the method of balancing. But if we go through the ion-electron method, it will take some time. It would take some time, and if we want to save that time, we can apply this technique. What we'll have to do, we'll have to find out change in oxidation number for one formula unit of oxidizing agent and one formula unit of reducing agent. So one formula unit means here must be 1, one formula unit means here must be 1. So for 1, 1 we want to determine the change. In this we have manganese, 1 manganese on the right side. So manganese is undergoing change from 7 to 2. Carbon is undergoing change from 3 to 4. So difference in oxidation number per formula unit is 5. Difference in oxidation number per formula unit is 5 for KMnO4. But it is not 1 for this, 1 for 1 carbon only. For 1 potassium oxalate there are 2 carbons, so 2 carbon plus 3 into 2 plus 6, here will be plus 8. We have to see it like this, C2O4 2 minus giving 2 CO2, then one formula unit will be accounted for, and then plus 6 plus 3 into 2 plus 4 into 2, 8, 6. So here we have difference of 2 in the oxidation number of oxalate. What you have to do, we have to find out the change in oxidation number for one molecule of oxidizing agent, one molecule of reducing agent. But saying one molecule is wrong technically. We use one formula unit because molecule is used only for covalent compounds, so it is ionic compound, so better we use one formula unit, but the sense is same, one molecule of KMnO4, one formula unit of KMnO4. One molecule of potassium oxalate, one formula unit of potassium oxalate. And then you just multiply by the, just cross multiply by the change in oxidation number. Cross multiplication by change in oxidation number per formula unit gives you a balanced redox reaction. So multiply it here by 2, cross multiplication here by 5, and that gives you a balanced redox reaction. See how? Once you have multiplied by change in oxidation number, cross multiplication by change in oxidation number, the coefficient of these two are fixed. Usually, to solve the stoichiometry, we require the coefficient of oxidizing reducing agent only, but if you want to balance it fully, that can also be done. 2 manganese, so 2 MnSO4, 5 into 2, 10 carbon, so 10 CO2. 2 potassium here, 10 potassium here, so 12 potassium, 6 K2SO4. On right side, now the coefficient of compound containing sulfates are fixed, so 2 sulfate, 6 sulfate, 8 sulfate, 8 H2SO4. 8 H2SO4, 8 H2 will be balanced by 8 H2O. It is 100% balanced redox reaction. So cross multiplication by change in oxidation number gives the balanced redox reaction. It's a magic. It's really magic. Let us take one more example. Let us take one more example of balancing. Say, let us take S8 plus K2CrO4 plus H2O giving K2SO3 plus KCrO2. Medium is alkaline, so wherever KOH is required, we would be using that. Here we have 8 sulfur, and each sulfur is in 0 oxidation state. On the right side, we have sulfur in +4 oxidation state. So for change in oxidation number on sulfur, we'll have to take like this, SO3 2 minus 8 sulfur for 1 unit. 8 sulfur will have to be considered. So on this side 8 per sulfur is +4. So 8 into 4 32, 0 to 32. So change here is 32. In potassium chromate, here we have 6, here we have 3. -4 + 1 -3, so +3. So change is of 3 unit. So cross multiplication by change in oxidation number, 3 here, 32 here, 3 here, and 32 here will give us the relation between sulfur and potassium chromate. Now balance the others. 3 into 8, 24 sulfur. So here must be 24 K2SO3. Sulfur is balanced. 32 chromium. So here must be 32. Now on right side we have 24 into 2, 48 potassium and 32 potassium. So 80 potassium on the right side, 80. We have 80 potassium on the right side, and on the left side we have only 64, 32 into 2, 64. 16 less. So 16 potassium will come here from 16 KOH. 16 KOH. So 16 KOH will come on this side. Now hydrogen oxygen. We have 16 hydrogen here and no hydrogen on the product side. So water will not come on the left side. It will come on the right side. And for 16 KOH, there will be 8 H2O to balance the hydrogen. The rest of the things are balanced. So actually, here 16 KOH will come, and now it is a balanced redox reaction. You can see 3 into 8, 24, so 24 sulfur. 32 into 2, 64 and 16. 80 potassium, 24 into 2, 48 plus 32, 80 potassium. 32 chromium balanced. Oxygen, hydrogen can be seen, 32 into 4 plus 16. If you add them, 24 into 3 plus 32 into 2 plus 8, that will be equal. The question is, can this shortcut method be used to balance the disproportionation reaction? The answer is yes. It can be used. Let us balance the disproportionation reaction using this shortcut method. Suppose we want to balance a disproportionation reaction H3PO3 in H2O giving PH3 plus H3PO4. If we can see, phosphorus is here in plus 3 oxidation state, minus 6 plus 3 minus 3, so plus 3. Here we have minus 3 and plus 5. Plus 3 to minus 3 reduction, plus 3 to plus 5 oxidation. So it is disproportionation. Now we want to balance it by shortcut method of balancing. What we will do, we will write the reagent undergoing oxidation as well as reduction twice, like this. And we will relate one with one product, another with another product. And then again we will find out the change in oxidation number here. So 1 phosphorus, 3 to minus 3, change of 6. 1 phosphorus, plus 3 to plus 5, change of 2. If there is any common factor in change in oxidation number, drop them, so it would be 1, 3. And again cross multiplication. This 1 would come here, and this 3 cross multiplication would come here. So what would we have? What we would have? 3 undergoing oxidation. So 3H3PO3 undergoing oxidation, and 1H3PO3 undergoing reduction, plus water that will take later, giving PH3 plus H3PO4. So 3 oxidation will give 3H3PO4, 1 will give 1. Now if we balance hydrogen oxygen, what we see, 3 into 3, 9 oxygen, plus 3, 12 oxygen. Here we have 3 into 4, 12 oxygen, so water will not come. Hydrogen is already balanced. 3 into 3, 9, 3, 12, 3, 3, 3, 9, 12 balanced. Now you combine these two. 3 plus 1, 4, so make it 4 and delete 1. It is possible to balance the disproportionation also by this method. Can we balance a redox reaction involving more than one elements of the same compound change in oxidation number? Yes. Let us take a redox reaction FeC2O4 plus KMnO4 plus H2SO4 giving Fe2SO4 whole 3 plus MnSO4 plus CO2 plus K2SO4 plus water. Iron plus 2, 2 plus 3, carbon plus 3, 2 plus 4. So both iron and carbon are undergoing oxidation and manganese is undergoing reduction. Can it be balanced by shortcut method? Definitely, 100%. What we'll have to find out? Change in oxidation number for one molecule of ferrous oxalate. That can be done in rough. Iron, there is one iron in one ferrous oxalate which is undergoing change plus 2, 2 plus 3. There is one oxalate C2O4 2 minus undergoing change to CO2. So for one oxalate 2 carbon will have to be taken on both sides. Here change is of 1 unit, here of 2 unit, plus 6 on 2 carbon plus 8 on 2 carbon. So net change of 3 unit. So it is undergoing 3 unit of change in oxidation number per formula unit, and per magnet change of 5 plus 7 2 plus 2. Balanced. Just multiply it here by 5, cross multiplication, 3. Rest of the things can be balanced. So 5 iron will be balanced here by taking 5 by 2. Now these two are the fixed coefficient. 5 into 2, 10 carbon, so 10 CO2. 3 manganese, 3 MnSO4. 3 potassium, 3 by 2 K2SO4. Now sulfate can be balanced. So 5 by 3, 15 by 2 sulfate here, 15 by 2, 3 from manganese sulfate and 3 by 2 from K2SO4. So 15 by 2 plus 3 by 2, 9 and 3, 12. So 12 H2SO4, there will be 12 H2SO4, and so 12 water also. So any type of redox reaction can be balanced by this shortcut method of balancing, which will be a very important and strong tools when we go for solving a redox reaction, stoichiometry of a redox reaction. So in the next lecture of redox reaction, we will be discussing the real stuff of redox reaction, that is stoichiometry of redox reaction, how we manipulate the stoichiometry of a redox reaction using the concepts of equivalence and normality, and then at the end redox titration.